Good morning, everyone. So we'll get started back here in chapter 4. We're on the oxidation numbers section. Last time we were talking about the difference between oxidation versus reduction. We might remember that oxidation is losing electrons, reduction is gaining electrons. So reduction is gaining, oxidation is losing electrons during the course of a reaction. If we're going to determine if a reaction involves oxidation and reduction, we have to know how to assign oxidation numbers so we can understand the charge states from an oxidation picture for atoms and molecules and in their elemental forms, so that we can understand if they've gained or lost electrons during the course of a reaction. And so this is a bookkeeping system. Sometimes the atoms will actually bear the charges of their oxidation numbers. For example, if we have calcium chloride, so CaCl2, then the oxidation numbers for ionic compounds are exactly the charges of the ions that we know. So the oxidation number of calcium's +2, just like its charge is, chloride's -1, just like its charge. And so for ionic compounds, it's actually pretty simple, especially for the simple atomic ions of determining their oxidation numbers. So the oxidation number for some compounds are just their charges. When we get into the molecular compound side of things like water, we're going to see that for hydrogen, by rule, we're going to assign hydrogen to have an oxidation number of +1 and oxygen of -2. And in the real compound, the atoms don't bear these charges. So we can assign an oxidation number, have a sense of which atom is perhaps more positively charged, which atom's more negatively charged. But in the real molecule of water, the atoms don't actually bear those charges, despite the fact we'll assign those as their oxidation numbers. So this is a bookkeeping system. It doesn't always imply that the atoms actually bear those charges. If we can sum up all the oxidation numbers of all the atoms in a compound, then that should equal the charge of the compound or ion. So for the case of water, if we go back to it for a minute, +1 for hydrogen, -2 for the oxygen. Overall, water is uncharged, so +1 times 2, -2, of course, is equal to 0. So we should be able to sum up our oxidation numbers and get the charge of something like water is neutral. And then we'll go through a system of rules. For a lot of our atoms, we can determine by rule their oxidation number. And then for other atoms, we can use inference from the summation of all the oxidation numbers going to the charge on the molecule or ion. Elements have oxidation numbers of 0. So if you have an element like O2, the oxidation number here would be 0. If you had F2, the oxidation number would be 0. So anything in its elemental form where you just have one element present, so no molecule, no ion here, these would just have oxidation numbers of 0. Obviously the same thing if you have iron solid, oxidation number would be 0 as well. Even like ozone, oxidation number would be 0, and something like ozone. So anything where it's just one atom, one element present without a charge, the oxidation number would be 0 for the atoms in that substance. Let's look at some other rules for oxidation numbers. So atomic ions always have oxidation numbers equal to their charge. So if you have an ion like iron 3+, then the oxidation number is just 3+. If you have calcium 2+, like we did earlier, the oxidation number, of course, is just +2. Oxide ion would be -2. So if you have a simple atomic ion, you know the charge and the oxidation number, they go hand in hand. Now, oxygen's rule in basically all other compounds would be that it's usually -2, but we're going to see that peroxides are an exception where oxygen has an oxidation number -1. Superoxides are another exception for oxygen, which have oxidation numbers of -0.5. And then compounds with fluorine are going to vary because fluorine's rule is that it's always -1 in compounds. So elemental fluorine, 0, but fluorine in a compound would be -1. So fluorine's not going to form a compound where it goes positive in charge. Fluorine's the most electronegative element that forms bonds commonly with other elements. So fluorine is the most electronegative. It wants electrons the most. It's the element on the periodic table that's never going to go positive in compounds. Hydrogen can be positive when paired up with nonmetals and molecular compounds, and it actually goes negative when it pairs up with metals and forms hydrides. So let's look real quick at a couple examples. The next slide has a lot more examples that kind of hopefully reinforce these rules. If we go through the oxygen, couple examples real quick. we could have with sodium, we could have sodium oxide, so Na2O from nomenclature sodium oxide, because this is O2 minus, sodium plus, two of the pluses, so we have to have a -2. So that's the ordinary oxide ion, -2 charge for oxygen. If we have the formula Na2O2, this is that case where still sodium has the plus, so 2 sodiums plus 2. This is where we have that O2 with the -2 charge, which I'm sure we remember from nomenclature as sodium peroxide. And so then think about the oxidation number per O. If the entire O2s are -2, so each one of the O's would be -1. So each O would have an oxidation number of -1. And so that's why peroxides oxidation numbers are -1. A superoxide would be something like sodium O2, NaO2, so we have a plus for the sodium, -1 for the 2 oxygens. So each O has a -1 charge divided by 2. So because we have 2 O's, the charge in each O is -1/2. So -1/2 times the 2 O's, -1 overall for the charge on superoxide. So -1/2 superoxides, the only one by rule that's fractional. All the other rules for our charges are some whole number. So it's the only one that we see that's a fraction on this page. An example of a compound with fluorine involving O would be something like OF2. And the key is almost like knowing which charge trumps the other. So it's the fluorine being more electronegative, wanting electrons more, that keeps it as its normal charge of -1. Oxygen adjusts its charge, therefore, to be +2. And so do you guys see how I'm really taking advantage of the fact that all these compounds in this row here are neutral in charge. So all their oxidation numbers have to sum up to 0 when we factor in the number of each of the atoms. So -1 times 2 for fluorine, and then +2, therefore, for oxygen. A couple quick examples with hydrogen. One would be like hydrogen peroxide. So H2O2 is hydrogen peroxide. So +1 by rule for hydrogen. So +2 for the 2 hydrogens, -2 for the 2 O's. That's the O2 2 minus. That's where the peroxide's coming from. So each of the O's here is -1. And then a simple hydride. In fact, the hydrides you would know are negative just by the rule that the metals are always going to be positively charged. So if you had something like calcium hydride, you know calcium's not going negative in charge. Calcium's always going to be a +2. So all of our metals are positively charged when they form ions. Our alkalis +1, alkalins +2. So we know calcium's a +2, so therefore hydrogen has to be a -1 charge and oxidation number here in this atomic ionic compound. So this would just be calcium hydride. Hydride was in our nomenclature. I don't think we saw too many examples of it, but we're just seeing this one here kind of play out almost from knowing the charges, from knowing the type of compound this would be from chapter 2. And so then fluorine -1, other halogens usually -1. And then when aren't the other halogens -1? Well, you can imagine when they pair up with O or when they pair up with F. They'll adjust accordingly. So like ClF3, so fluorine's always going to be negative. So -3 for the 3 chlorine, or for the 3 fluorines, therefore a +3 for chlorine. And then ClO3 minus. A few of these examples are on the next page too, but ClO3 minus, the oxygen keeps its -2. There's no exception for oxygen when it pairs up with chlorine. There is for fluorine, but not for chlorine. So oxygen keeps its ordinary -2, 3 of them, but all the charges have to go up to -1 here because this is a -1 charged ion. This is the chlorate ion. So we're summing up to -1. Therefore, the charge on chlorine has to be +5. So we go +5 -6 for the 3 O's to -1. And so for peroxides, superoxides for oxygen, those are only forming with hydrogen peroxide. Hydrogen superoxide isn't really a thing, so you'll never see HO2. That's not a stable enough molecule to exist and bottle and sell and ship like you can hydrogen peroxide. And then with metals, the peroxides and superoxides only with alkali and alkaline metals. They're not forming with other metals that you don't know the charge of already. So you can spot an alkali or an alkaline peroxide or superoxide just by knowing the charge of the alkalis +1, alkalins +2. So most of our other atoms that aren't on this set of rules here, we can determine by inference, just by knowing the other charges of the other atoms involved in the molecule. molecular ion. Okay, so this chart here, I mean, most of these are pretty straightforward, right? Because these are all just elemental forms. So these are just zeros. Helium, noble gas, of course, 0. Bromine, liquid, elemental form 0. We already did the hydrogen peroxide, so +1, -1 for H and O and hydrogen peroxide. Al2O3, the only thing for oxygen is thinking, is this a compound with fluorine? Of course not. Is it a peroxide or superoxide? Can't form one with aluminum. So this is just ordinary oxide ion. We also know aluminum has to be a +3, and then those charges do check out. So +6, -6, uncharged, so that's good. Calcium nitride, we know this should be a +2. In fact, we may not know this is a nitride, but once we double check our charges, +6, -6 for the two O's, so -3, so N -3 is nitride. +2, -2, calcium sulfide, just in the oxygen group. Barium hydride, like calcium hydride, barium's an alkaline. So you see, these aren't super challenging. The key is like knowing which atom to start with. Like when I look at NH3, I know I start with hydrogen because it has a rule that it's +1 when paired up with nonmetals. And so therefore I can get nitrogen by inference here to be -3. So -3 for nitrogen, +1 for each of the three H's. O2F2 is another compound with fluorine, so fluorine again stays negative. So we have a -2, so we have to have a +2 for the two oxygens. So there's two oxygens, so therefore +1 for each. One thing I recommend is put the oxidation numbers up top and then do your math below, just so you don't confuse the math for your oxidation number. Like if we were to write these, the math above, we might think those are the oxidation numbers, and that's just our balancing and accounting for each of the oxidation numbers for the number of atoms. KO2. So starting with, we know potassium has to be a +1. That's how we get the entire O2 group has a -1. And so therefore each O is -0.5. You could also have said, well, that's potassium superoxide. I know superoxides are -0.5 as well. So you can get to the -1/2 a couple of different ways. This one looks like a peroxide, and it is. I have a -2 shared among the two oxygens, so that's a -1 for each of the O's. So for ionic compounds, the charges are more or less what we expect from our oxidation numbers. So the charges for ionic compounds kind of go hand in hand with their oxidation numbers. With molecular compounds, not exactly the case. So the charges on carbon and oxygen and CO2 really aren't -2 and then +4 for carbon, but it becomes a bookkeeping system. It becomes a system that carbon's the more positively charged atom in this molecule of CO2, and then oxygens are going to be the more negatively charged atom in those molecules.
Question.
Yes?
KO2, oxygen is having half.
Mm-hmm.
I thought the charges cannot be after the whole number.
No, that's just, it's not entirely true, because oxygen here, we have two oxygens bonded together where the entire group shares one minus charge. So like O2 with one negative charge is the charge of the superoxide ion. If you remember from like naming, we had this ion here is the superoxide ion, where you just have a -1 charge being shared between the two atoms. So it just turns out that the math works out to be a fraction here. There's a few other compounds that can work out to be a fraction as well. So the charge can be distributed among two atoms, and that's completely legal. So it's okay that it's a fraction. It's not very common. There's none other that by rule are fractional, just this one oxygen and a superoxide being -0.5 by rule. Like if you look at, I think if we were to look at like an alcohol, there's some type of, I think maybe C2H6, like if we have ethanol, I think carbon works out to be a fraction there too. So if you look at C2H5 with the OH group, you have a +1 for hydrogens by rule, -2 for the oxygen by rule, so you end up coming up with +5, -2, +1. So this is still going to be a whole number. There's some type of compound that has a fraction too. I can't remember which one it is, but there's some type of compound that's relatively common where carbon ends up with the fractional oxidation number. But in this case here, this would be a +4, so -4 for a -2 for each of the carbons in ethanol. Okay, so for MnO2, the key here is that it's not a peroxide or superoxide, is the first thing I want us to think. Is when I look at MnO2, I don't have to look at the O first and worry if it's a peroxide or a superoxide. I have to look at the O's and know that they're just ordinary oxide ions. So if we remember, peroxides and superoxides are only forming with the alkali and alkaline group. And manganese is a transition metal. So these would just be ordinary oxygens with a -2 charge, 2 of them for a -4. So this is manganese 4 oxide. We saw examples in chapter 2 of like titanium 4 oxide with the same thought process. So let's not confuse ourselves. If we have a peroxide or a superoxide, we'll know those O's charges because it has to come from an alkali or an alkaline cation. MnO2 is on there twice, I guess. Copper chlorate. So we know how to get copper as a copper 2 from chapter 2. So we know that's copper +2, so oxidation number +2 for copper. And ClO4 minus, let's just break this down for one ion like we did ClO3 minus before. -2 for the 4 O's, so that's -8. So we have to have a +7. Just remember we're summing these up to the charge on the ion. So chlorate's a -1, so +7 for chlorine. Now you could have count for 14 for the 2 chlorines and then minus 8 times 2, so -16 for the 4 times 2 for the 8 oxygens. So you could have 14 minus 16, that's a -2, copper +2. So we could break down this math and account for a chlorate, one of them with a -1, or we could use the 2 chlorates -2 charge and just double the math and still get the same oxidation numbers. So we can break this math down a few different ways. I think if you know an ion, you can work out the oxidation numbers of each of the atoms using the ion's charge. You just have to make sure that you use the proper charge for the ion. Here, chlorate -1. ClF3, we did this earlier, -1 +3. CCl4, -1 by rule. Chlorine goes by rule. Carbon doesn't have a rule. So to figure carbon out, we have to look at the other elements first. The way we would tell is you'd have to have something like potassium or something like calcium paired up with the oxygen, where you would know that metal's charge first. So like the +1 for potassium or a +2 for calcium, then you could work out here that this would be a -2 and that this would be a -1, but for the collection of the 2 oxygens. And so if you had any other metal where you didn't know the charge of the metal first, then those metals don't form peroxides and superoxides. So like transition metals just don't form peroxides and superoxides. So that's why with manganese we didn't have to worry about having one of those 2 other compounds. So kind of go by rule, oxygen's -2, but with the exceptions, peroxides, superoxides, compounds with fluorine. And so we just have to rule out that manganese and things like in the transition metal row aren't going to form peroxides and superoxides.
So it's only the first row, or the first column that will form the O2, like -1.
Yeah, usually. And then I don't think you can get even the alkalins to form the superoxides. So like I don't think you're going to ever get CaO2. But theoretically, I could see it in an example. We could still figure it out, but I don't think we'd see something like CaO2, because I think that's how we'd write the formula as opposed to CaO4, because we're really trying to stress you have the superoxide ion twice. Okay, so CCl4 -1, so -4 for the 4 chlorine, so +4 for the carbon. KNO3, what would you start with KNO3? Obviously the K, right, for plus. The oxygen -2. And so what would nitrogen be? So +1 +5 -6 goes to neutral, so +5. So we just have to know which atoms we start with. The atoms we start with were on the previous page. Hydrogen +1, metals, -1 nonmetals, oxygen usually -2 with its exceptions, fluorine -1 always, other halogens usually -1. Okay, let's work on this compound. Let's have you guys work on this one together for a minute or two. So which compound below contains chlorine with an oxidation number of +1? So which ones can we probably most easily roll out? So I think we can probably most easily roll out C, because those have to be 0, elemental form, so it can't be C. I think we can easily roll out D as well. We know with nonmetals, hydrogen should be +1, chlorine should usually be -1, so +1, -1 works here, so that's not +1. We saw chlorate earlier, but ClO3 with a minus charge would be a +5, because we have a -6 here, -1 overall, so that's how we got the +5. And so then this one here has to be the one that goes to +1. The way that this would work out here would be NaClO, ordinary +1 sodium by rule, ordinary O -2 by rule, and so then we have to have a +1. So for +1 minus, so the two pluses added together, -2 goes to neutral. Okay, so it'd be NaClO would have that oxidation number of +1. Now, we want to use these oxidation numbers to help us determine if a given reaction is an oxidation reduction reaction or if it's not. And the way we can spot an oxidation reduction reaction is by spotting something being oxidized and something being reduced. And we can then hopefully identify which atom's being oxidized, which atom's being reduced. And then we can even define a slightly different word than we've used before in defining which substance serves as the oxidizing versus reducing agent. But we'll talk about this in a minute. So for the first two reactions, are they redox reactions, they oxidation reduction reactions? So for the first reaction, I think it is, because we have 0 charged sodium, 0 oxidation number chlorine reacting to form +1, -1. And so the sodium is that sodium gaining or losing an electron? It has to lose an electron to pick up the positive charge. So sodium underwent the loss of electron, so oxidation is losing. So sodium is oxidized. So sodium lost electrons, oxidation is, I keep spelling oil, O-L-L, oil. So sodium is oxidized here. So it's oxidized in the reaction, and chlorine goes from 0 to -1. So it picks up an electron. So each chlorine gains an electron, so chlorine here is gaining. So reduction is gaining. So chlorine here is reduced. Okay, so we can spot which atoms oxidize, which atoms reduce if we know their charges and can work them out for the reaction. So for the second reaction, we have zinc 0 going to zinc 2+. That's the only charge we know for zinc is a +2. And then we have iron +2 because of the two nitrates. So nitrates are, of course, minuses. So nitrate's not changing. Iron's going to a 0. And so nitrate goes to nitrate. So without working out, and we did it earlier too, so I'm sure we remember +5 and -2 for N and O is a nitrate. But we don't even really have to work out nitrate because nitrate's the same on both sides. So nitrogen or oxygen are neither oxidized or reduced in this reaction. And so, of course, the zinc is losing electrons. So zinc is oxidized, right, 0 to +2. And then the iron is the atom that undergoes the reduction. So iron is reduced. Usually you look at the element, you say the element of iron is reduced in the reaction. You're not necessarily saying iron 2+ is reduced per se by nomenclature. You're usually just looking at the element, saying which element in the reactants is oxidized or reduced into the products. And so usually these are properties that you give for a particular element. And I'm just going to erase that little underline so that we don't think I was writing Fe- or anything like that. So iron is reduced. Now, in terms of the term agent, an oxidizing agent is actually reduced in a reaction. The oxidizing agent is the substance that facilitates something else being oxidized. So an oxidizing agent facilitates the oxidation of something else by itself being reduced. So an oxidizing agent this is the substance containing the reduced atom. In that reaction. And it's the substance in the reactants. tip came unscrewed. There we go. We're good. There we go. Okay. So the stupid tip came unscrewed. Okay. So the oxidation is a substance in the reactants. We're not looking in the products and defining a product as the reducing agent or the oxidizing agent. We're looking in the reactants and saying which substance contains the atom that was reduced. So the atom, let's look in the second reaction. So let's look in the second atom and determine these substances that serve as the oxidizing agent. So the oxidizing agent contains the atom that's reduced. So the oxidizing agent would be iron nitrate. Now, you're probably thinking, why is the atom that's reduced called the oxidizing agent? Or why is the substance that contains the atom that's reduced called the oxidizing agent? Well, think about this. Is the agent of a movie star a movie star? Probably not. Is the agent of a sports star a sports star? Maybe they were before, but they're usually not currently. Like LeBron kind of maybe is, but that might be a weird exception. But usually you think of the agents are the facilitators of and not the thing. And so the facilitator of the oxidation allows something else to be oxidized, which means it has to be reduced. And then the only difference, the only reason why you have the definition of which atom's oxidized versus which atom's reduced is usually you look at those on an atom by atom basis. So we're looking and saying iron is the atom that was reduced. And usually the oxidizing agent is the entire substance. It's like the entire thing you would actually add to the reaction. So usually it's something you're classifying the entire thing. So you would say like iron nitrate AQ is the entire substance is the oxidizing agent. And not just the iron within it, even though iron is the atom that undergoes the reduction. And so then by corollary, the reducing agent is the substance in the reactants that contains the oxidized atom. So it's the substance in the reactants that contains that oxidized atom, so that would be zinc solid in that second reaction. So zinc solid would be the reducing agent. And so the word agent just kind of flips which one's oxidized versus reduced, but it's because it's the facilitator of that thing. So the oxidizing agent is reduced, and the reducing agent is oxidized. Okay, and again, I think you see the difference of the terms used for the agent being applied to the entire substance, and then the atom, we just apply to the elements that are being oxidized versus reduced. If we look at the first reaction, so sodium is oxidized, so this is our reducing agent in the reaction. So the vernacular usually goes, sodium is the element that's oxidized in the reaction, therefore sodium solid serves as the reducing agent. Chlorine is the atom that undergoes reduction, is reduced in the reaction, so Cl2 gas is the oxidizing agent. So again, think of the agent applying to the full substance, and then oxidized reduced just applying on an atom by atom or element by element basis. Okay, so then the last thing in this chapter is, in this section, this is not the last thing in the chapter, so the last thing in this section of the chapter is on comparing different activities of metals and their relative ease of oxidation in water. And so lithium is among the most easily oxidized elements on the periodic table. Most of these are metals. There's one non-metal on this chart of hydrogen. And so lithium has the highest ease of oxidation, so the ease of oxidation is highest towards the top of this chart. And then things like magnesium, aluminum, manganese, or transition metals are kind of in the middle. And then metals towards the bottom of the chart here are metals that you tend to think of as usually existing in their metallic form over here, rarely in their cation form. So these are our more precious metals, so things like gold, platinum, mercury, silver, copper. These things are precious because they don't easily oxidize and then therefore dissolve. So you probably don't want to dissolve gold. In fact, I used to do a demo where I would like put my gold ring into an acid solution to show that it wouldn't dissolve, and it doesn't. But so you probably don't want your precious metals dissolving easily in water or an acidic solution. And then our acid is kind of right in the middle above these coining metals. So our precious metals, right above those is actually our acid H plus to H2. And so the way this kind of chart works is if you were to take the metals at the top, usually they more commonly exist in their charged state. Usually when you encounter sodium or lithium, it's sodium chloride or in some sort of solution containing their cations. You can have, of course, the metal. So it's not that you can't have these metals. It's just that if you put the metal in contact with solutions below them containing those cations, you're going to have a reaction take place. So we can use this chart to predict that if we take metals from this side, or cation solutions from this side of the chart, and mix them with metals above them, then a reaction is going to take place and they're going to switch sides. So we're going to have an oxidation reduction reaction take place. If we try to do the opposite, if I tried to take like a solution like lithium, and if I put lithium cation with gold, nothing happens. But if I put lithium with gold cations, gold's like, give me that electron so I can go back to gold. So the next slide will go through examples on how we can predict when reactions take place using this chart. And so will copper dissolve in zinc sulfate, or will zinc dissolve in copper sulfate is a question we have. So for the first question here, we're kind of looking at copper. So we have copper here. So is copper going to react with the zinc cation, which is here, or is zinc going to react, or will zinc metal react with the copper cation here? So let's write out the two reactions and think about how we can use the activity series to predict which one of those reactions actually takes place. So the two reactions we might write out, the first one will be Cu solid, so copper, reacting with zinc sulfate. Now, if they were to react, this is an oxidation reduction reaction, so our zinc is going to form. If this reaction takes place, we'd have zinc form and then copper sulfate form as the byproduct. So we have copper 0 going to 2+, and we'd have zinc 2+ going to zinc 0. So does this reaction take place, or does the opposite reaction take place, the zinc solid plus the copper sulfate going to copper solid plus zinc sulfate? And let's throw a few AQs in here. So the sulfates are the aqueous water-soluble ionic compounds. Metals are just metals, so like think of having a chunk of copper. So we don't have water solubility. In fact, most of your transition metals aren't soluble in water. And so, okay, so it comes down to relative activity. So we would want the metal here to be more reactive than the metal so we'd want to start with something that's reactive so that something that's less reactive can go back to its metal. So copper is more stable. Copper wants to reform here. Zinc is more reactive. So zinc is higher up. Zinc solid is higher up than copper. So we're going to take zinc and form copper. So we're going to take something that's more reactive and produce something that's less reactive. And that's exactly the reaction that occurs spontaneously, would be this reaction here. And then the opposite reaction is just not going to occur. So we get no reaction when we mix together copper and zinc sulfate. So we can use the chart to say that copper, being less reactive, can't possibly form its cation to give its electrons up to something like zinc to go back to zinc. So we can't start with something less reactive and produce something more reactive. So you're comparing the two metals' activities here. You want to start with something more reactive and then produce something that's less reactive. Maybe next time I'll get this demo so I can show you guys that we can drop gold into HCl and then show that it shouldn't react and that it doesn't indeed react. So gold is down here. So if we take gold, Au, and then put this into a solution of H+, now gold, if it were to react, would form 3+. So if we zoom in here, you can see that that's gold 3+. So gold 3+ would form if this reaction were to take place. H2 would form for hydrogen. So we'd have 3 H2, 6 H pluses. We need 2 and 2 to go into balance, just to have whole numbers here. because of the two H2s. But it doesn't really matter because the H pluses can't go back to hydrogen because gold's not reactive enough. So gold has a lower reactivity than the hydrogen we're trying to produce here, therefore no reaction should take place. So we can predict what the reaction would be if it were to take place, and then look at the relative activities of the gold metal, look at the two different elemental forms of hydrogen versus gold. Gold's not reactive enough. So gold's lower down, hydrogen's higher up, so we can't produce the more reactive H2 with the less reactive gold. Yes?
Hydrogen is not even on the list.
Hydrogen is in the blue list. I just have written too much on top to see it. So hydrogen is that blue one right in the middle.
Oh, thank you.
Yeah. And blue is shown for hydrogen because it's the only non-metallic. Everything else is metallic on the chart. Hydrogen's the one non-metallic element that's shown on this chart. Okay, so this is using the activity series to help predict when oxidation reduction reactions occur. Just remember, you want to start higher up on the metal side. You want to start with metals that are more reactive to produce metals or nonmetals that are less reactive. Okay, there's a slide on another example of this. I think it would actually be better to take a break, maybe see that next time and go through an example once we let that settle for a bit. So let's come back to an activity series problem once we get to the end of the notes. Let's move on at this point and start talking about some concentration units. So molarity is our main unit that we talk about in chapter 4. You might remember learning molality as another unit. I don't know how many of you guys learned that in high school, versus percent compositions and percent by volumes and things like that. Those are later concepts that you'll learn in chapters 13 and 16 later in the class. But molarity is our main unit for concentration here in chapter 4. And molarity is the moles of a solute that's dissolved in a certain volume of solution. And it's a really useful and easy to determine value. You would usually put so much substance that you know a mass of your solute into a container and use like a volumetric flask where you can very carefully know the total volume of the solution. The reason why it's important to maybe note the difference between the volume of the solution versus volume of water is if you have a lot of solute, you might not have to add the solution volume in terms of water. Like for example, if you're trying to dissolve 200 grams of sodium chloride into a liter of water, that you may not have to, or into a liter of total solution, you may or may not have to add precisely a liter of water. But it doesn't matter how much water you have to add. What matters here is usually using a volumetric flask. This is my terrible drawing of a volumetric flask. Say it's a 1 liter flask. So you put your sample, your solid into here, you add water into the flask, you start dissolving the compound, and then you precisely come up to a point where you have 1 liter of solution. And that may or may not be the addition of a liter of water. And it doesn't matter how much water you add. The key is how much total solution you have. The way molarity works is you want to use this value with how much volume of solution that you have. So if you have 25 mils of the solution you're going to use, you can easily multiply your moles per liter of solution by the volume used to tell you how many moles of your solute are in that solution. So let's look at a few different problems on solving for what a molarity is and how we can use molarity in some problems. So what is the concentration? So we'll often say, what is concentration? Either moles per liter or molarity of 0.250 moles of sodium hydroxide dissolved into 200 milliliters of total solution. So the molarity, big M, would be the moles of our solute, moles of sodium hydroxide dissolved into the volume of solution. We usually just go into the volume in liters. So we'll go 0.2000 liters for mole per liter. And so this should be 1.25. Now we can explicitly write this out, moles of sodium hydroxide per liter of solution, or we can write this 1.25 capital M. So capital M equals 1 mole of your solute per liter of solution. So we'll use that big M a lot. So like 1.25 capital M is interpreted to be, if it's 1.25 molar sodium hydroxide, it's 1.25 moles of sodium hydroxide per liter of solution. So it's going to be key that we know how to think in moles per liters to help us do problems as we go. So a lot of times a problem might say capital M, but it's going to be helpful in problems sometimes that we write out mole per liter explicitly. That'll help us do dimensional analysis and get some of our math straight later. Like for example, like if we're asked how many moles of sodium hydroxide are present in 37.5 milliliters of 1.25 molar sodium hydroxide. So M, I usually say molar if I'm saying it out loud. And so like the vocabulary would be molar is usually the kind of vernacular that you might say to express that if you're reading it out. So 1.25 molar sodium hydroxide. If we're trying to solve for the number of moles of sodium hydroxide in this solution, I would start with the 1.25, but write this out explicitly. The reason why I would write this out explicitly is it makes sure that we multiply by the 37.5 as opposed to divide by it. So it's liters of the solution. So I know that I need to multiply by 37.5, but in liters. To get the volume to cancel. So 1.25 times 0.0375 would be 0.0469 moles of sodium hydroxide are present in that 37.5 milliliters of that solution. Now, dilution is how we can change the concentration of a solution by adding just the solvent. Our solvent here, of course, is just water. So we can lower concentration by adding water. And so what's being shown here is, like, let's say you have 25 mils of a 1.00 molar stock solution. It looks like some sort of copper ion solution, probably because copper is blue. And so then if we take 25 mils of that solution, put it into a volumetric flask, like this one here, it's a 250 mil volumetric flask. It just means it has a little notch, and if we fill with water, then the total solution in that container would be 250 milliliters. And so if we add 25 mils, fill to the line with water, and again, it's probably going to take 225 mils of water, but it doesn't have to. It can take whatever volume it takes to get to that line. Sometimes solutions don't mix exactly as you expect. But then we dilute with water until the solution reaches that calibration mark, the 250 milliliter mark, and then our concentration would be cut by a factor of 10. Now, how is that, or how can we show that our concentration went from 1.00 mole per liter to 0.100 mole per liter? Well, we could show that really one of two ways. One way would be thinking of how many moles there were. Uh-oh. Well, it doesn't help. If any. Okay. So if we have 1.00, this is moles per liter. Think about how many moles of the solute. We don't even know what the solute is, but the moles of the solute would be 1 mole per liter times 0.025. So this is 0.025 moles. Just from taking the moles per liter times the volume of 25 milliliters. Now, when I add that to here, the moles of my solute aren't changing. So the moles of my solute in my final solution is still 0.0250 moles. So I'm not changing the number of the moles of the solute by diluting. I'm just changing the volume of the solution. So instead of this being 25 mils, as it was before, it's now 250 mils. 0.250 liters is now the volume of my solution. So 0.025 divided by 0.25 is 0.100 mole per liter. So the way a dilution works is we're not changing the moles of the solute, we're just changing the volume of the solution. Now, there's an alternate way, there's where I want to write this. Let me write this here. So what's really going on, if we think of moles, so moles, we usually use the symbol N. So our moles, we get that by taking the the molarity of our solution times the volume of the solution. So if we multiply those two together, we get moles. And so if we think about the moles of our solute, that the moles of the solute aren't changing in a dilution. So if I'm doing a dilution step, I have the M initial, V initial, so what initial volume I had in its initial molarity. So in this case, the 1 molar and 25 milliliters. And then if I think about the final molarity times the final volume, that these have to be equal to that same number of solute moles. That these moles here aren't changing. So the moles of solute are the same before and after our dilution, because we're just adding pure water. And so if both MiVi equals mole solute, and the mole solute's the same, so that equals MFVF, then MiVi has to equal MFVF. And then VF here is our final volume of the solution. And it's just making sure that we make it clear that it's the final volume of the solution, not the volume of added water. And so we added probably 225 mils of water, but it's the 250 milliliters of the total solution that matters at the very end. So what matters at the end is that we're filling this solution to be 250.0 milliliters. And so if we think of the MiVi equals MFVF equation, sometimes M1V1 equals M2V2, what we end up with in this case here would be 1.00 molar times 25.0 milliliters equals our final molarity, which we're going to solve for, times our final volume of 250.0 milliliters. So 1 times 25 divided by 250 gives us a final molarity of 0.100 mole per liter. And then I didn't have to convert milliliters to liters as long as they were in the same unit. I could have converted both to liters, but they both are milliliters, and milliliters will cancel out here. So as long as VI and VF are in the same unit, then they can be in whatever unit they're in. We don't have to convert units. And so, but this works just because the moles of solute is what's being constant before and after our dilution step. So we can use this equation. We can use the idea of moles is just molarity times volume. We can solve problems. Equation approach that we can use, trying to see a variety of ways. Okay, so let's look at this dilution problem here. So we have 37.5 mils of a 1.5 molar HCl solution diluted to a total volume of 250 milliliters. What's the concentration of the new solution? Method 1 might be saying, well, let's figure out the moles of HCl, and then let's divide by our new total volume. So that was kind of the first approach we used. Our second approach might be the MiVi equals MFVF, and just plugging in our Mi, our Vi, and then our Vf to a total volume of 250 liters. And so we either have to convert liters to milliliters or milliliters to liters. So let's do 0.0375 liters times 1.50 mole per liter, and have this equal MF times 2.50 liters. So I just needed the two volume units to be in the same unit as each other. So my MF is 0.0225 mole per liter. So we reduced the concentration of our solution. So notice, of course, molarity's dropped due to this dilution step here. Now, let's go back to the concept of electrolytes, that HCl really isn't in the solution, right? So HCl is not really the solute particle in this HCl solution. H plus and Cl minus are the solute in the electrolytes in the solution. So what's the H plus concentration? What's the Cl minus concentration? Well, we get 1 mole of H plus per mole of HCl. We get 1 mole of Cl minus. So each of these ions would have a concentration of 0.225 moles per liter. Now, what if I had a solution that was the same concentration? Let's actually use a different. Let's say we had 1.0 molar calcium chloride. So we have 1.0 molar CaCl2. What's the concentration of chloride ion in that solution? So Cl minus brackets is kind of the concentration in molarity units. So we'd get 2 moles of chloride per mole of CaCl2, so this would be 2.0 moles per liter. So we have 2.0 moles of the chloride ion per liter solution, so 2.00 m, or 2.0 m. We could also look at the total ion concentration. So sometimes we say, well, what's the total concentration of ions in the solution? Let's go back to the HCl solution. So that would just be the 0.0225 times 2. So this will be 0.0450 moles of total ions. The electrolytic nature of a solution goes higher, but like a light bulb would light up brighter if we had that light bulb example, the more ions we have. So this solution here will be less electrolytic than, say, a 1.0 molar solution of HCl that had a higher concentration. So the more ions we're getting per liter, the greater the electrolytic behavior of the solution. Okay, so conductivity proportional to total ion concentration. So the more ions, the greater the conductivity of a solution. So which solution here, if you have a mole of each of these compounds, we take 1 mole of each, put into the same quantity of water, which compound gives you the greatest electrolytic solution? Well, we get plus and minus here, so we get 2 ions here. Here we get 2 ions as well. Here we get 3 ions. So calcium hydroxide goes to the 2 hydroxide and calcium. We get 3 ions for aluminum chloride. So all these are water soluble. We get 4 ions here. So we get more moles of ions with AlCl3. So the electrolytic nature depends on how many ions a solution has to give off. Okay, I just want to head to next. So the last section in chapter 4, we'll wrap this up, get into chapter 5 next time on dealing with stoichiometry of solutions. So the last section looks a lot like chapter 3, but just dealing with stoichiometry problems with mole to liter conversions with volumes. Okay, so we'll look at this last section on Friday and also get into chapter 5. Have a great day, everybody.